So now we're going to switch gears and change over to polar coordinates. So we've talked a little bit about polar coordinates with derivatives, but now we're going to work with double integrals in polar coordinates. So from previous knowledge of polar coordinates, we know that x is r cosine theta. These are just formulas. Y is r sine theta. R squared is equal to x squared plus y squared. And tangent theta is y over x. This is probably pretty helpful to write down somewhere to reference as we move throughout the course. So I can use polar coordinates to describe a region. When I do that, I'm describing arcs and circles with what I have. So for instance, in the first one, I'm describing the arc of a circle that has a radius of 2 and it's 90 degrees. So from 0 to pi over 2, or from 0 to 90 is the region that I'm describing. So the region R being a quarter of that circle, that's how I would describe it, and how I would use that notation is that I would have coordinates r comma theta, where r is between 0 and 2, because as I go from 0 up to 2 up here, that's going to be how I generate that curve, and from theta is 0 to pi over 2 is what generates the actual arc piece. In the second part, the region R looks a little bit different. It's concentric circles. So if you look at these two circles, the innermost circle has a radius of 1, the outermost circle has a radius of 3. And so the way I would articulate that is I would say, well, the radius is between 1 and 3. Because it's a complete circle, I have 0 to 2 pi or 0 to 360 as my region. So those are just descriptions of what polar coordinates look like. Now, what's new and what's extended into our knowledge is going to be polar sectors. So I'm going to have regions that are described by the area between two polar segments. And so if I look at this figure, I have the area R, and I have my r theta, that's like saying f of x, and I have it between r1 and r2, and then between theta 1 and theta 2. I don't have to know exactly what those values are, but this is basically how I would describe them. Once I know those values, I would plug in the numbers. To define a double integral of a continuous function, I'm going to introduce the variable z just like we did in the derivative section. And I'm going to consider the region R to be bounded by, again, two functions in theta, and the lines theta equals alpha and theta equals beta. Now, why do I have that description? Because I'm bounding it by arcs. That's why. Instead of cutting up those regions into small rectangles like we did in Calculus 1, I want to use a partition of small polar sectors. So this is kind of close to Simpson's rule when we're looking at this. Kind of close. On R, I would imagine a bunch of little sectors, which are kind of like, if you were drawing them by hand, they'd probably look sort of trapezoidal, right? But I am trying to basically create graph paper in this. So I'm kind of superimposing to get that nice look that I see in that piece. The polar sectors, so little sectors of the curve, within that R are entirely within that region bounded by the two curves. And it's called an interpolar partition whose norm, using the double brackets, is the length of the longest diagonal of the polar sectors. And so if I consider this, it would be shown by what I have here in 14.27. Now, it's a little bit hard to consider the longest diagonal, so it may not be obvious to you, but generally when I'm at that middlemost point, the distance from corner to corner is going to be the longest. So I can show this in a couple of different ways. I can say that my area is going to be that r sub I times the change in r sub I and the change in theta, where the change in r sub I is r2 minus r1, should look familiar, b minus c, and theta 2 minus theta 1. So I have two ratios that are happening here that I'm subtracting. This implies that the volume of this solid would be found by the following equation. which is where the double integral comes in. And the sum notation is going to be a Riemann sum. So in practicality, am I going to use these formulas? Yes and no. In practicality, this is more theoretically. Now, if I connect this to what I already did, let's look at this image and say, well, this is horizontally simple. I'm bounded by something on the left and the right, so it's horizontally simple. So because I'm in polar, I can't have the dx on the outside of the parentheses. I have to do something a little bit different. So in this case, my dA is in the outside of the parentheses. And so from this concept, I land at this formula, which tells us that we are going to treat r as a constant at first, and then theta as a variable. Then when we integrate the second time, we're going to treat r as the variable and evaluate between the bounds. So to simply state this in a concise block that you could screenshot, it would look just like this theorem right here. So the region is being restricted by two basic types here and this version. So this is another version of the same thing. I have what we're calling an R simple region and a theta simple region. Just like the horizontal and vertically simple, if I look at the difference, the R simple region is like a vertical, I say like a vertical, kind of like a tilted vertical rectangle. But if I'm looking at the theta simple region, that's like a strip. So kind of like a striping on a ball is the way to think about it. This is going to change the way we treat something as a constant and something as a variable. No different from what we did earlier. So let's see it actually in practice. So I've got this region, and notice I have the R simple region here, okay? And because I have the R simple region, that means that I'm going to have my dA at the back. That means also, if I look at my polar boundaries, they gave them to me here, which is super nice because it's not an even radius value. I'm going from 1 to square root of 5. So my polar boundaries are 1 to square root of 5. And because I have a complete circle, I'm going from 0 to 360. Something else. X squared is r cosine theta squared. And then y would just be r sine theta. I have to plug in. I can't do x's and y's here because I'm in polar. So now what I have to do is I have to integrate with respect to what I'm dealing with. So if I'm looking at this, I have r squared cosine squared theta plus r sine theta times r dr d theta. What I'm going to do is I'm going to multiply that r in so that I don't have a product rule in that integral. Then I'm going to integrate with respect to r being a variable and theta being a constant, which is where 1/4 r to the 4th comes from. Cosine squared theta is just a constant value. Same thing is true with sine theta. Then I have to integrate my thetas, which gets a little trickier. So from there, I have to integrate using my trig functions and then plug in my theta value of 2 pi and plug in my theta value of 0, which is how I arrive at 6 pi. If you're not quite sure on the integration of those trig functions, I do encourage you to revisit the integration section to make sure that you understand how we integrated those pieces. So you would be utilizing the Pythagorean triples there to be able to get to that actual integral statement.